Hello and welcome to Maclearn 360. In this video, I want to explain to you or introduce you to rotating unbalance. So what is rotating unbalance all about? So this is where we are actually going to start from. Now let's consider a system. Okay, let's say I have a system where I have a mass. Okay, let's say this is my mass. And then I attach some spring to this system. Then I have a damper. And then this is actually connected to some support. Okay. So this is my K, and then this is my C, right? Okay. And then this is my mass. Let's assume that I want to constrain this such that there are rollers, all right? So let's say that there are rollers right here. And these rollers are such that the vertical motion of the mass is only permissible. So the mass can only vibrate in this direction. It cannot go this way because of the rollers. Now, what happens is that for this system, it's going to actually vibrate, okay? But whenever I want to get some unbalance whilst the system vibrates, then what I would do is that we normally attach. So let's say this is a shaft. This is a point of connection with the shaft. Then I have what we call an eccentricity. So E is called eccentricity. When we say eccentricity, eccentricity simply means the distance away from the axis of the shaft where I attach a small mass. So let's say this small mass is M. And this small mass will be rotating with a certain frequency called omega. All right. Now what happens is that the angle form, okay, so let me just do the here as theta, okay? So we know that angular speed is theta over t. So I can say that t equals what? Omega t. So this, theta. So this theta right here is actually omega t, right? Okay. Now what's going to happen? What's going to happen? So in fact, what's happening is that if I have a system like this, and then I connect this whole system to a support, as I begin to rotate this small mass, because this small mass is attached at a certain eccentric distance or eccentricity from the shaft, and this is inside the mass, what happens is that it's going to cause the mass to be rotating. There's going to cause an unbalance. So there's going to be a certain shaking. So the mass will be shaking like that. And as this small mass rotates, our mass will be shaking. In fact, this is what we use in our compactors. This is the mechanism inside all compactors, okay? All the road compactors, right? All the road compactors. And some of the machines which are doing the sieving mechanisms, sometimes you want a shaking force. The idea is that attach a small mass at a certain eccentricity on this shaft and connect it to this mass. As this small mass rotates, we are going to actually get some shaking force. And in this video, I will explain to you the shaking force as well as the force. Don't forget that if this is going to shake, then we expect that there is some force which is going to be transmitted to the support, right? So let's look at what we are going to do right here. This is where we start from. So to begin, we are going to draw the free body diagram, okay? We are going to start with a free body diagram. So now let me start from free body diagram. All right. So the first thing I want to do is to take the mass. So let me take the mass that I have right here. Now let's say this is the mass. Watch this. Watch this. I want to take the small m outside so that what I have will be the difference. Okay. So in other words, for the purpose of analysis, I want to take the small mass out. Okay. I want to take the small mass out. So if I take the small mass out, then the mass that will be left will be m minus m. Don't be confused. All what we are trying to say is that this mass, which is supposed to be initially here, we want to take it out for the purpose of analysis. Therefore, if I take something out, I need to illustrate it by minus m. It means I have taken it out. And that's why this now becomes m minus m. But since this is a point of attachment, let's say a hinge, there's going to be a reaction. So let's say there's going to be reaction along the x. Let's call this reaction Rx. And then there's going to be some reaction Ry, right? So we are looking at the free body diagram. Is that right? Now what happens is that, so let's say that, per these rollers over here, what happens is that my mass can only be doing some displacement in this direction. It cannot be doing this. So let's assume that we have given this mass some displacement, let's say x of t in the upward direction. Okay, so let me ask you, now if this mass is pushed forward, because of the spring and then the dampers here, what do you think will happen? Yes, you are right. Because this spring and this damper is connected to the mass, if I push the mass up, the spring and the damper will push it back, right? And so the spring force is going to be coming downwards in this direction. This spring force is given by kx, and then this one is also given by cx dot. All right. Now, Sir Isaac Newton is saying that since the mass and the base is, or the support, so this is the support, is actually connected by the spring. Newton is saying that, okay, so the floor will also give some equal but opposite reaction. Okay. So in fact, this is actually the free body diagram as far as the mass is concerned. Is that right? However, don't forget that I have taken the small mass. So let's look at the free body diagram of the small mass. So the small mass will also come here. And Newton's third law, right? Since the attachment, so the reaction over here is this one. So on this one, it will be equal but opposite. So Rx, rather it will come here. And then over here, Ry will rather come here, equal and opposite forces, right? Now over here, watch this. We are saying that there is this eccentricity, and we said that the eccentricity is the distance which is actually away. So the shaft, there's a shaft, and then the shaft along the axis of the shaft, there's a distance, and this distance we are calling the eccentricity. And then we have attached a mass here. Okay, we have attached a mass here, which is small m. Now what we are trying to say is that there is an angle here, which is omega t. And this angle omega t here, so I want to ask you a question. Watch this. You see, this small mass is inside a big mass. It means that the total displacement of the small mass is going to be the displacement from the big mass plus the small mass, its own displacement. Are you with me? I'm saying that the total displacement is that of the small mass plus the one inside it. And so we expect that the displacement of the small mass is going to be what? This side, using trigonometric ratios, I'm going to get E sine omega t. That is this side. It's going to be E sine omega t. But the total displacement, which I expect to get, is actually the displacement from the big mass, which is, let's say, some x, right? This is this x, and then what? Plus this one is also some form of displacement. So plus E sine omega t. And this is actually the total, displacement of the small mass. All right. Having known this, then I think we are good to go. So let's start from the big mass, okay, the original mass we have here. We are going to say that summation of forces along the x going up is positive should be equal to mass times acceleration. But over here, because we have taken the mass out, it's going to be the big mass minus the small mass. So the big mass minus the small mass is equal, x dot dot, right? All right. Let's sum the forces in the positive x direction. Let's go. So now let me do it y. Sorry, there is no motion along the x. It's actually the y direction. Now it's going to be, it means that this ry, okay, this ry is one of the forces. So I'll say that positive ry because it's going up. Then kx, so kx is also coming down, right? So minus kx. And don't forget that there is also cx dot here. So it's going to be minus cx dot, right? Is there any other force in that direction we have not considered yet? No. So it should be equal to m minus m x dot dot, right? So let's solve for ry. So we can say that ry equals m minus small m x dot dot plus cx dot plus kx, right? Let's call this equation 1. Let's call this equation 1. And let's come here, okay? Let's come here. We are going to do the same thing for this one, okay? So maybe I can even do it here. We want to sum forces in the positive y direction to be equal to, so for this one, this is the small m, so it's going to be mass times acceleration, okay? All right. Now, let's look at the forces. Let's look at the forces. So it's going to be ry, but look at this time around, ry is coming down, right? You can see that clearly ry is coming down. So it's going to be, that is minus ry. This one is coming down. And then, that's all, right? That's all. Should be equal to mass times acceleration. But what is the acceleration? In fact, if we want the acceleration, we need to differentiate this total displacement here. Okay, so maybe let me call this total displacement. So the xt, the total displacement, is actually, as a function of time, is actually x plus e sine omega t. Now the first derivative, we want the double derivative. So the first derivative, x, if I differentiate x, I'm going to get x dot. And if I differentiate this, I'm going to get, so the omega will come out, right? And then if I differentiate sine, I'm going to get cosine. So it's going to be e omega cosine omega t. Is that not it? And that is the first derivative. Now, if I do the second derivative will be what? X dot dot plus, no, sorry, minus. Because if I differentiate cosine, I'm going to get negative sine. So it's going to be minus e omega squared sine omega t. In fact, this is the double derivative we are after. Therefore, I can rewrite this as m multiplied by x dot dot minus, so in fact, this x dot dot that you see here of t is the double derivative of the total, okay? Don't be confused. Someone will ask, but there's x here and there's also x here. This x here that you see is the total displacement, but this x here is due to only the big mass, and this displacement is due to the small mass. That's why we have added them together. So we are going to get e omega squared sine omega t. Having gotten this, then I can clearly say that my ry from here, so okay, minus, so let me just do it this way. minus ry is mx dot dot minus me omega squared sine omega t. So that is my ry. All right. Having gotten this ry, what did we say? We initially said that ry is this. You know what? If this is equation 2, then we can say that we can equate them, right? Because this is ry, this is also ry. Therefore, I can say that m minus m x dot dot plus cx dot plus kx should be what? The same as this one because it's also r. But it's going to be, so the ry over here is going to be minus what? Mx dot dot. But this one is going to be plus. Is that right? Plus me omega squared sine omega t. You know, this is coming from here, right? Let's try to play around this. So I'll get big mx dot dot plus cx dot plus kx, and this will be equal to, you know, the small m is minus here, so it will come here to become plus, right? Then I'll have me omega squared sine omega t. At this juncture, what we are going to do is that mx dot dot plus cx dot plus kx is equal to, so this will cancel this. Then I'll get me omega squared sine omega and t. Having done this, then what I'm going to do is that, in fact, I have gotten an equation right here. And this is similar to a forced damp system. For a forced damp system, the equation will take the form f naught sine omega t. And so I can say that f naught is equivalent to mu squared. And in fact, this force over here is actually the shaking force or the dynamic force. So we said that, so this is what we are trying to say. This force that we have just discovered, me omega squared, is the dynamic force which will give us the shaking. So what we are trying to say is that this small mass will give us some shaking force, and that shaking force is given by that. So whenever you are asked a question on rotating unbalance and you've been asked to calculate the dynamic force, that is the mu squared. So I call it me omega squared, which is small me omega squared, where E is the eccentricity. Okay. Now, so I'll leave the link below so that you can watch the video on forced damp systems. For a forced damp system, again, we can show that the amplitude of vibration, which is x, so we can show that the amplitude of vibration for this one, which is x, is given by f naught, all divided by, so f naught all divided by square root of k minus big M squared, big M omega squared plus C omega squared. We can show this for a forced damp system. That is the amplitude. So we call this the dynamic amplitude. Okay. The dynamic amplitude. And this is going to be ME. So the F naught we are saying is ME omega squared. Then I'm going to divide the whole of this by the square root of what? K minus big M omega squared plus C omega squared. So I'm going to make here ME omega squared. All right, so over here we have gotten the amplitude, but let's try and play around it. I like playing around equations. So let's try and play around this equation. So if I attempt to divide through by, K, okay, let's divide through by K. So it means that I'm going to divide through me omega squared, all divided by the stiffness K. Then I'm going to divide this through by K divided by K minus big M. Um, and then what? So big M, and then omega squared over K, and then all squared plus C omega over K squared. Okay. Now, what happens is that, sorry, what happens is that the amplitude of my rotating unbalance, the amplitude over here is going to be, so what is this quantity here? So watch this. Now, if I have omega squared over K, omega squared over K is what? Watch this. I want to rectify this. We know, so okay, let me put it this way. So we know that the natural frequency squared is K divided by M, right? And so if I have, okay, this is K over M, and we also know that, tau squared is omega over omega n, okay, squared. So in other words, I can say that omega n squared is equal to what? Omega n squared, omega squared over tau squared. So from this equation, and then from this equation, then I can say that my my omega squared over tau squared is the same as K divided by M. So if I have omega squared over K, all right, so if I have omega squared divided by K, then this quantity is nothing but tau squared divided by big M, right? And in fact, these are all coming from the pulse damp vibrations. Let me tell you this. There is a difference between the small m and the big M. They are not the same. They are not the same. The small m is the unbalanced mass, and the big M is the mass of the system. So this is what I'm saying. The big M is this mass of the system that we have, and the small m is the unbalanced mass, which is giving us the unbalance. Okay. So what can we do? What can we do right now? So we've been able to show that omega squared over K is tau squared over big M. Therefore, I can rewrite this as X equals ME divided by M, right? Then I'll say that tau squared all divided, okay, let me write it here. So I can say that my amplitude is ME divided by M. Then I'll multiply it by tau squared all divided by, K. So K divided by K will be 1. And then, so we just saw that K over M is omega n squared, right? So if I divide this by this, if I have M over K, then M over K is nothing but, inverse of omega n squared. So I will end up getting tau squared. In fact, I'll end up getting omega squared divided by omega n squared, which is what? Tau squared. So tau squared, and then, and then plus, in fact, we are going to get, there is a square root. Oh, my bad. There's a square root here. So this tau squared plus 2 zeta tau squared. Where from the 2 zeta tau, it can be shown that C omega over K is the same as 2 zeta tau. And you get all from the pulse damp vibrations. That's why I'm saying that I urge you to watch that video. Now over here, we've been able to express a certain quantity here. And this quantity is what we call, the amplitude of our vibrations. Okay, this is actually the amplitude of our vibrations, and so the amplitude. All right, since we now have the amplitude, let's try and calculate let's try and find the force transmitted to the support. All right, so let's calculate the force which is transmitted to the support. Now, this is what is going to happen. So this is what we are saying. Let's go back to the diagram. All right, so we are saying that, if I have a system like this, as this force is shaking like this by the small mass, then we expect that there is going to be a force transmitted to the support due to the unbalanced force. We recently established that F naught is what? We said F naught, which is the shaking force, is me omega squared. All right. Now we are saying that there is a force which is transmitted to the support. In fact, this F naught is what is transmitted to the machine. Okay, the F naught is what goes on to the machine, and the Ft is what goes to the support. All right. Now, from a force balance here, clearly we can see that Ft is balanced by what? Kx and Cx dot. Can you see that? This is going down, this is going up, this is going up. So we can say that our F of t is balanced by Cx dot plus Kx. Now, if I have a system like this, I can actually assume a solution, and the assumed solution of this is actually some x, some x sine omega t minus theta. Why am I assuming this solution? This equation is similar to a force damp system. All right, so I'm standing here, and then I'm saying that this solution is actually similar to a force damp system. Since I have the damper present, then I expect my response to take this form, where this is actually the amplitude. So this is the amplitude. Okay, this amplitude over here, this one. Okay. All right. Now let's find the first derivative. So the first derivative is going to be x omega cosine omega t minus theta, right? Okay. Now, since we have this and then we have this, we can say that our Ft is a combination of C omega x cosine omega t minus theta plus K x sine omega t minus theta. Since I have cosine omega t and I have sine omega t, then I can go forward and say that the magnitude of Ft is going to be C omega x squared plus K x squared. Is that right? So that I can actually write this as my Ft is my x squared C omega squared plus x squared K squared. Okay, so Ft will be what? Square root, and the x will come out to come and multiply K squared plus C omega squared. But this is actually the force which is transmitted to the support. Interestingly, what we are trying to say is that this is the force that goes to the support, where this is the dynamic amplitude, my stiffness squared, plus C omega squared. Okay. So over here, what have we been able to do? We've been able to find the force transmitted to the support. Is that right? Okay. Now, this is very much interesting. Is that not it? I like playing around equations. Again, let's play around some equations. This time around, I want us to find a certain quantity, and this quantity is actually called the transmissibility. The transmissibility. The transmissibility. Okay. So let's do this. So this is the force transmitted to the support, all right? Force transmitted to support. That is this force we have here. So in the exams, or we are solving any question, and you've been asked that find the force transmitted to the support, then you are going to use this, equation. All right. Yeah. So let's look at the transmissibility. So transmissibility. The name sounds weird, but it's actually simple to understand. So your transmissibility is nothing but your ratio of the force transmitted to the support against your dynamic force. In other words, what fraction of the force is transmitted to the support? What fraction of the force is transmitted to the support? That's what you want to ask yourself. Now, if you want to know that, since we know Ft and we know F naught, then we can play around something, right? So let's do that. So watch the Ft equation clearly. You can see that Ft is x into what? K squared plus C omega squared. But what is x? It is interesting to note that the x over there is actually this x. From first principles, the x that you see there is actually this x. Interestingly, I can just say that, so that is my x, f naught over square root of k minus m omega squared plus c omega squared. So it's going to be what? F of t is going to be f naught all divided by, so this is all xo. Interesting. So f naught all divided by the square root of k minus m omega squared plus c omega, that is x. Then I'm going to multiply this by square root of k squared plus c omega squared, right? So over here, what I'm going to do is that I'll stand at here and divide this ft by f naught, right? Interestingly, if I do that, the expression that I'll get is what we are calling the transmissibility. Sometimes we also call it the transmissibility ratio, TR. So in fact, I'm going to get something like this. So it's going to be what? If I take the square root thrown out, then it's going to be k squared plus c omega squared all divided by k minus m omega squared plus c omega squared. And this is what we are calling the transmissibility ratio. Again, I like playing around equations. So let's play around this equation again. If I play around this equation by dividing through by k, then I'm going to get k divided by k all squared plus c omega divided by k all squared. And then I'll do divided by k over k minus m omega over m omega squared over k all squared plus c omega over k. And then I'll square all this. right, under the root sign. Then my transmissibility ratio will be K over K is 1. So it's going to 1 plus, in fact, C omega over K has been already shown to be 2 zeta tau. So 2 zeta tau all squared. And then I'm going to divide this by 1 minus, and what is m omega squared over K? In fact, that is going to be tau squared, and plus, again, 2 zeta tau. You see, all the time, the C omega over K is 2 zeta tau, and then m omega squared over K is what? In fact, we have done it already here. So that's why I didn't do it again, right? We've been able to do all this, and we were able to get this. So we know the amplitude now, and now we've been able to find what we call the transmissibility ratio. All right. So in fact, this is actually the end of this lecture video. But in the exams, or if we are solving any question, you have to be very, very smart and be very careful. Depending on whatever parameter you've been asked to find, you should know what to do. Sometimes they can give you a transmissibility ratio, and they will ask you to solve for maybe the damping ratio, or maybe solve for the natural frequency, or maybe solve for the frequency ratio, any of them. But this is the equations, right? Then the rest is just your mathematics. All right, so thank you very much for watching this video.